This is my first finite element analysis video in about 6 years, after spending that time in an Abaqus recovery clinic. Today we're going to be looking at how to create a model for steel reinforced concrete and loading it beyond its elastic limit. To try and connect this tutorial with something from reality, I'm going to loosely recreate one of the reinforced concrete supports from this bridge in Germany. I posted this picture onto the Germany subreddit to see if anybody could identify the location of the bridge for me. As it turns out, Germany has many more bridges than I would have guessed. The first part we're going to create is the concrete pillar. And we're going to be operating in units of meters. Our default size, or approximate size, will be 3 meters. And we'll take these default settings here, so 3D deformable solid extrusion. Continue, and going to start by drawing 2 circles with a radius of 0.4 meters for both of them. Connect the top and connect the bottom. And then I'm just going to trim the parts in between. Okay, so that's our structure. Sorry, that's the shape. We're going to give it a depth of 5 meters. Okay, so now we have the concrete pillar. I am going to add some partitions to this just to make the meshing neater when we get around to that. So partition cell, we'll do it by 3 points. So I'll split it this way first. Okay, so in half that way. And now I'm going to split off the 2 semicircular sections. So I'll just highlight the whole thing. 3 points again. I'm going to do this right side first. So 1, 2, and then the 3rd point up here. Now select the cells to partition. We'll do the same thing on the left side. 3 points again. 1, 2, 3. Okay. So we're finished with the modeling of the concrete pillar. Now we'll go on to the reinforcement bar. We'll just call it rebar. This time it'll be a wire. And yeah, that's okay. And I'm going to give it an approximate size of 5 this time, because it's going to be the same length as this. Okay. Now draw the line and yep, dimension it, confirm that's 5 meters, that's fine. And okay, so that's our wire created. Sorry, the rebar created. Next thing we'll do is create the stirrup. Again, we're going to pick a wire for this. Approximate size can be smaller for this. I'm just going to say 2 meters. And it'll essentially just be a rectangle. The bottom side is going to be 1 meter long, and the sides are going to be 0.4 meters. And just middle click to create that. Okay, so that's done. And now we have our parts created. Now we're going to start on creating our material properties. The first one I'm going to create is concrete. For the actual material properties that I'm using in concrete, if I can figure out how to link to other videos in YouTube, I'm going to do just a quick walkthrough on what these properties mean and how they impact the model. And that link should pop up here if I can figure out how to get that to work. I'm just going to be adding materials now talking about them in the other video. So we'll have a mass density of 2,400 kilograms per meter cubed. Young's modulus of 20 gigapascals and a Poisson's ratio of 0.2. Then I'm going to be adding a concrete damaged plasticity model to this. So a dilation angle 31 degrees. This will be 0.1, 1.16, 0.67, and 0. For compressive behavior then, I have a table here with values that I'm just copying and pasting from. Again, these values I'll be talking about in that other video that I linked to earlier on. That's our compressive behavior, and now for our tensile behavior, it's a little more straightforward. Yeah, so, okay, as you'll see, compressive behavior and tensile behavior are different for concrete. You probably know that anyway. Okay, so I'm happy we've the material created for concrete. Now we're going to move on to steel. The density of 7,800 kilograms per meter cubed. Give it a Young's modulus of 210 gigapascals with a Poisson's ratio of 0.3. And we're going to add some plasticity to this as well. Again, I have a table of values here, but okay, that was wrong. It's much smaller than the table for the concrete material. I'm just going to delete this row. Okay, so that's the material for the rebar and the stirrups. They'll be using steel. Now that we have the material created, we're going to create our sections and then assign the sections to the parts. Okay, so create section. The first one is going to be our concrete section. And yes, work away with the default values. Material is concrete, that's fine. Create a new section. This is going to be the rebar section. And it will be this time in the category of beam, and it'll be a truss. So we'll have to assign it a cross section. So first of all, okay, material is steel. The cross section we'll use is 0.000819. This is just kind of a standard cross section that I found when looking up standards for rebar. Again, I haven't worked in real life with concrete or rebar, so I don't really know what you would use on this scale of structure, but this is something from real life anyway. And create our last section, which is for the stirrups. Again, that'll be from a beam category and truss type section. It'll be steel material, and typically the stirrups are significantly lower cross-sectional area compared to the reinforced bar. in this case, I'm going to use 0.000387 meters squared. Okay. So we've created the 3 sections. Now we have to assign it to the parts. So open up concrete first, section assignments, assign a section. Okay, just had to double click that. Select the region to be assigned a section. So that's all of this will be concrete. And okay, that's fine. Now we go to the rebar, section assignments, all of this, and that will be rebar. Okay. And you know where this is going, so into stirrups, section assignments, highlight all of this, and it is stirrup. Okay, so that's applied, even though this is just a wire, that's applied a cross-sectional area to this. We're now going to move to the assembly module, create our first instance, which is the concrete pillar. That's fine. Now we're going to add our rebar. It's auto offset. That's fine. Okay, obviously we can tell that the rebar is rotated the wrong direction. Should be going along the concrete. So the first thing we'll do is rotate the instance. So select the instance, and I'm going to rotate it along an axis here. So we'll have our start point, our end point. Default angle of rotation of 90 degrees is fine, and middle click just to accept its new position. There's a point that's automatically generated between at the midpoint of this particular line here. That's where I'm going to be moving this rebar to, translating it there in a moment. First of all though, I want to put an offset datum point from here, which I'll use as a reference point for my stirrups. So use the offset datum tool, select this point, and I'm going to be moving minus 0.25 meters in the z-axis. So that creates a point here. That's fine. Now we're going to translate this bar. So select the instance, select the start point of the translation vector, now the end point, and middle click to accept. So if we turn on transparency and pull this down, we can see our reinforced bar inside this. Okay, however, now if I want to pattern this, select the instance to pattern. I can't easily select the rebar, so we're going to hide the concrete. So part model instances, select the concrete and remove it. So it's just hidden for the moment. So now select the instance to pattern. I want to pattern the concrete bar. Yeah, for some reason it's given a weirdly low number here. I'm going to be patterning this 0.4 meters apart in direction 2, and for direction 1 I'm going to have 5 and 0.25 apart. So I'll accept that. I'm happy with how that looks. Now if we add the concrete back in, we can see the pattern of our bars going through the concrete pillar. Now we're going to repeat all this with the stirrups. So add my instance of the stirrup. That's okay there. And I'm going to hide the concrete again and translate this to that point. So using the translation tool, select this instance, select the start point of our vector. This reference point here will be the end. Okay, and now I'm just going to pattern this stirrup all the way up through the column. So select the instance. And I have to change the direction. So it's going out in the X direction, and I want it to be along the Z direction. Okay, that's in the Z direction, but the opposite way, so we're going to flip it. And it will be 0.25 meters apart. And we're going to have 19 instances of that. And that evenly spaces them out throughout the column. Okay, so now we'll show everything again, replace all, and turn on some transparency. So you can see the reinforced frame that's going up through the concrete pillar. That's good. The next thing we're going to do is move to the steps module, and here we're going to be creating our step, set and history output. So okay, we'll create the first step, and yeah, these default values are fine. Incrementation. I'm going to change this just for this particular example because I want to get, rather than completing the whole thing in just an increment size of 1, I just want a few different data outputs. Minimum is fine, maximum 0.05 as well. Okay, that's fine. Obviously, with your model, you can do whatever you'd like here. So we have the step created. We'll create our set, and these are going to be the sets that will extract our load displacement values from. So tools, set, create. We'll call the first one reaction set, and that's going to be the bottom surface of this, so just holding the shift button while I'm selecting multiple surfaces. So that's the first set created. Tools, create set. This one will be the displacement set. So I'm going to be applying a pressure on the top surface. So I just want to see what the displacement of this surface is. Again, holding the shift button. Okay. And now to create the history output, I call the first one reaction output. From step 1, continue. It's from a certain set, it'll be the reaction set. And I want to get the reaction forces in the Z direction. So reaction force 3. Okay. And now I'll do the exact same thing again. This time for displacement output. From step 1, set is this time the displacement set, and I'm going to be getting displacement again in the Z direction. We'll move on now to creating our interaction and then our loads. So I'm just going to establish an interaction between the embedded parts, which are the stirrups and the rebar, and the host, which is the concrete. So select embedded region. So it says to select embedded region. All this is basically so as you can establish the relationship between the parts that are inside a host material. Another example of this, or where you could use it again, is in if you're modeling a composite material, embedding a fiber into a matrix. Okay, so it says select the embedded region. That means we have to hide the concrete pillar, remove that, dismiss, highlight all of it, middle click to select. Now it says select method for host region. We want to just show everything again and hold shift. Select these regions, middle click, and I'm just going to use the default settings for the embedded region constraint. Okay, and now we'll move on to loading. So we'll start by establishing our boundary condition. I'm just going to use an encastrate condition on the bottom surface. So select that, select the bottom surface, encastrate. Okay, and now for our loading, I'm going to apply a pressure onto this surface in the Z direction. Loading, that'll be in step 1. I'm just going to make sure that the boundary condition was applied in the initial step. Yeah, that's an initial, okay. So loading in step 1 will be a pressure. Select the surface for the load. That will be up here. Middle click, uniform pressure, and I'm going to put in pressure of 5 megapascal, which when it's spread over the 1.3 meter squared surface area is equivalent to about the mass of 90 fully grown Tyrannosaurus rexes. So we'll hit OK. To create the mesh, we'll go into the mesh module and see the, we'll go in through the individual parts. So seed part, for this particular model I'm going to set a seed size of 0.08. Apply that, okay, and mesh the part. Okay, and because we did our partitioning earlier, these semicircles are nice and neat. If you didn't, you'd find that they wouldn't be quite as neat as that. We'll go into the rebar, mesh that. We are going to have to change the element type for these wire parts. So mesh element type, select the region, it'll be the rebar. And we'll scroll down to a truss and accept that. Select the element type, the region. Okay, that's fine. And now mesh, seed part 0.08 again. Okay, and mesh the part. And now we have to do the exact same thing to the stirrup. So mesh element type, because it's a wire, I'm going to go down to truss. Okay, that's done. Now seed part 0.08. Okay, and mesh the part. Okay, so now we've created our mesh for all 3 parts in the assembly. Scroll down and create our job. So double click on that. concrete rebar. I'm just going to call it that. That's okay. Continue parallelization. If you have a few cores you can use on your computer, the more the merrier. In my case, I have 16 cores. We can hit OK then. And we're ready now to submit the job. Open this, right click, submit. And let's see how it works out. I'm going to go into the monitor and just track this. That's completed for me now. So we'll right click on it, go to results. Okay, so we're not seeing much in here. Most of the stresses look like they're going to be inside. If you go to PEQ, just to see, it'll highlight material that is yielding. For example, now if you go into create display group, we'll go to results, result value, field output, okay, plastic strain, up to a max value of 0, and remove that. Okay, now we'll see all the elements that are beginning to yield. So this is at the end of our time scale. Looks like most elements have begun to yield. Looks like yielding starts at around the 0.4 time scale frame. Okay, so we're going to extract our reaction force and displacement information and just plot that. So we're going to XY data, our history output, and just going to select all the reaction force, reaction set items, save as, turn off plot curves on OK, save it as sum, and we'll just call this reaction. Okay, and then we'll select all the displacement ones from the displacement set, save as, turn off plot curves and OK, and this time it will be the average displacement we're looking at. And hit OK again. And dismiss. Now we want to operate on the data. Operate on XY data, continue. We have our two data sets here and we want to combine them. Oops, I clicked combine too many times. So combine displacement, reaction, and because of the sign of the reaction, if you just give it a minus, it'll plot it in a positive fashion for you. Plot expression, cancel. Okay, so this is our load displacement graph for our reinforced concrete pillar with the weight of about 270 fully grown Tyrannosaurus rexes on it. Honestly, I would have expected a little more yielding. Go back over the material properties and units here. Do your own research and make sure that you're selecting the correct material parameters for this. Honestly, I've no idea how well a concrete pillar would hold that many dinosaurs. Okay, so we can see here on the graph roughly at about a displacement of 2.5 millimeters, it looks like we're getting yielding. So I want to find out just where that is in the time scale. So if we go to Tools, Query, Probe Values, and it's around here that I think it begins to get nonlinear. And we'll just look at the reaction set data. So edit that. So I had an y value of 1.364. So 1.364, that's at the time frame of 0.7. Okay. So if we go back to this, okay, so this is our time frame at 0.7. So we do have yielding of elements before that. We can see it starts at 0.45. But it really isn't until time frame of 0.7 that we see it impacting the low displacement results. Just the yielding must be significant enough there to be visible, at least looking at that graph. Okay, go back to stress, and I'm going to show everything once more. The next thing I'm going to do is just to show you how you can visualize the bars that are inside here, because they're just wires normally, and if you turn on transparency, you can barely make out the stresses in the wireframe here. It's difficult enough to see. So if you go into options, common, no, sorry, that's the wrong thing. View, ODB display options, and turn on render beams at a scale factor of 1. There we go. So you can see them thicker now. This is the actual dimensions that I put in for their cross-sectional area earlier on. I just want to hide part instances, concrete, remove concrete. Okay, so now you'll get a bit of a clearer image of what's going on with the actual reinforced frame inside this concrete pillar under that particular loading. Anyway, I hope you've enjoyed or learned something from this tutorial. I know I have.